Okay, your exams are not graded. I'm working on it. Basically, the issue comes down to there were 20 of you that either did not have your clickers linked to your profile in Point Solution or Canvas or something, and so I'm having to go through and add you all line by line by line by line and grab your grades from the day of the exam. It's taking a while. Basically, what's going to happen is when I post grades, for the 140 of you that had everything set up correctly, you'll see your grade posted. If you're one of the 20 that did not have things set up quickly, to grab your attention, it will show up as missing on the day that I post grades, and then I will come back and I will add your grades when I can get to them and grade them by hand. I'm just doing that to catch your attention so that way this doesn't happen for the next exam. See my announcement from yesterday about what that will look like going forward. But if it shows up as missing, please don't send me 20 emails. I'll get to it. It's just going to take me a while to get to those exams. Okay, without further ado, we are ready to dive into our new unit. For the people in this class who are electrical engineers, we're finally getting into something that you're at least familiar with. As you log in, I'm curious to know your answer for what is the meaning of life, the universe, and everything. You'll notice that there is one answer, there is one correct answer. If you haven't read Hitchhiker's Guide to the Galaxy, it's a pleasure to read. One of my favorite pieces of literature is when the nuclear warhead becomes a whale in the middle of the sky with the infinite improbability drive. It's a pleasure to read that this author dedicates on whatever was going through his mind at the time, whatever was happening. He dedicates 3 whole pages to giving what the whale that's just popped into existence, what its thoughts might be. It really is a lot of fun to read. In fact, I kind of want to just pull up the audiobook on my way home today and just start listening to it. Especially all the stuff about politics of building an intergalactic highway and how we'd had 50 years to prepare for it, but didn't. I don't know. It's fun. Anyway, moving right along, let's talk about current. Current, we're going to discuss, is going to be how charge moves. How charge changes with respect to time would probably be the better way to describe it. So electric current is defined as the rate of flow of charge through a surface. So if you imagine this nice little silver wire here on the right-hand side of the screen, then through a cross-section area of that wire, you have these 4 little bitty charges Q that are passing through that cross-sectional area A. So we define the change in charge with respect to time is going to be equal to our current, and because we are physicists, we don't want to use things that make sense. We want to name things the way we have control here, so we denote current with I, and we use the physics notation, not little I like stubborn engineers do. We use big I to denote current, not lowercase I. I, lowercase I, is the imaginary number as far as I'm concerned. I is equal to dq dt when we take the derivative, or at least as far as the instantaneous current is concerned. And this is going to have current units of ampere, where 1 ampere is equal to 1 coulomb per second. And if you click the link there, if you have any interest in this whatsoever, I'm fascinated by the fact that the fundamental unit, as far as the SI system is concerned, is not the charge, it's not the coulomb, it's the ampere. Because up until recently, the ampere was what was measurable in a lab easily, not the coulomb. It's hard to measure the coulomb value, the charge value, of one individual electron. So we say the ampere is the fundamental unit, and the coulomb is just an ampere second. So the coulomb is the derived unit, the ampere is the fundamental unit. That's starting to change a little bit. They haven't changed their fundamental definition. Now the coulomb, or the ampere is defined as how many coulombs pass through a given, I don't know, it's interesting. We can't decide on what's more fundamental here, but we're getting there. So this is closely related at the molecular level with what is called drift speed. Inside of a wire, you have the high density of metallic atoms that are inside of there, and you've got the electrons, which are allowed to drift very quickly through there, or not so quickly. It turns out that the electrons, even inside of a copper wire, silver wire, gold wire, move very quickly, like on the order of hundredths of the speed of light. But the problem is then they bump into, or they're scattered by all the different nuclei and other electrons inside that wire, and you get a net drift speed that actually tends to be very low. So as electrons move through a conductor, they must navigate the dense atomic landscape, and their motion becomes stochastic. Stochastic is a mathematician and physicist word, fancy word for random. It bounces around in all these different directions. The current can be redefined in terms of this motion, where the current is going to be the charge of the charge carriers. So if your charge carrier is an electron, that would be that would be E. We're talking about the magnitude here. Times the number density of charge carriers. How many charge carriers can you fit per cubic centimeter, per cubic millimeter? Times the cross-sectional area A of your wire, or where it's traveling, times the drift speed, the drift velocity. So Q is the charge of the charge carrier. If it's an electron, that would be E. N is the number density of carriers. A is the cross-sectional area of the wire. And V sub D is the drift speed of the objects inside of your wire. Or you can get something like, I think nitinol and like carbon nanotubes. You can actually get crazy fast electron drift speeds. What's the graphene? Graphene has really high electron drift speed. We still haven't figured out what we can do with it that's cost effective, but graphene's still a really cool material. If you don't know what graphene is, it's basically a one atom thick layer of carbon crystal. Yes, William? Charge per carrier, not the net charge in the volume. Yes, charge per carrier. The current carried by a wire A is twice the current carried by an identical wire B. In which wire do the charge carriers have the higher drift speed? Please put wire C. I love that that's all on there. Thank you. I appreciate that. This is where we are in physics right after an exam, right? Like the choices are A or B, and for all we know, it could be Y or C. The correct answer, for those of you who weren't in on the joke on Y or C, the correct answer is A. So as current increases, assuming all of the other values are the same, meaning the wires are the same material, same size, same shape, the higher current corresponds to higher drift speed because current is equal to Q times N times A times V. So with them being related to one another, as current increases, assuming all other parameters are the same, drift velocity increases. So you're in the lab and you're pumping a 1 amp current through something, you would expect the net movement of electrons through that wire to have a certain speed. Say 1 centimeter per hour is actually what like normal drift speed through copper wire. 1 centimeter per hour. You bump the current up from 1 amp to 2 amps, you go from 1 centimeter per hour to 2 centimeters per hour. Now you're really booking it. A slug would be jealous of that pace. We can divide our last equation by area to get that the current over some area is going to be equal to what we tend to work more with in upper level physics. This is going to be called the current density. J is the current density, and note that it is a vector. The current density is going to be charges times their number density times the velocity, not their speed, but their velocity that they have. I find talking with electrical engineers, this is a weird concept to think about. But we've seen the cool things where Tesla sends current flying through the air with the greatest of ease. But current doesn't have to travel through a wire, right? As an astrophysicist, the way that I think about it is there are hydrogen clouds all through space, and some of them tend to be ionized, especially if they're in the region of stars. So you have these ionized hydrogen clouds that are traveling through space. They're not traveling through any sort of wire. If I map each one of those individual ions and their net motion through space, then that would be J. J would be how those charges are traveling through space. This is known as current density, and it turns out that the reason that we work with J, being a vector quantity, we go back to things like we did in Gauss's law, very similar. But if we know a current density, you can integrate over some area, say this area A here. And if you integrate the current density, all of the different charge carriers and their motion through this plate of area A, then that is going to end up being our current I.
Is it possible to make wires that don't have interference that are just like reluctance to try to straightforward?
So a superconductor is going to have zero resistance or really low resistance, and we'll talk about that here in a second, but no, there's still going to be bumping around unless, I don't know, that would be a fun material science project, right? Like if you could create some sort of really great crystal and create some sort of superhighway for the charge carriers. I don't know. I have like zero knowledge of material science. Maybe there is one out there. Maggie? The normal vectors, so when we take a differential area, then that's the same as taking the magnitude of that differential area times the normal of where you're doing that differential area. Up here, Bill. S, I probably should have put A. It's old habits die hard, right? So that's the integral over a surface. And normally I would put ds here instead of dA, meaning the differential surface area. But S is just the surface, the integral over the surface S here. I think I followed it this way because that's how your book has it listed. They've got a differential area over a surface. But in upper level physics, you'd see more consistent. Either it would be the integral over the area with a differential area or the integral over a surface of a differential surface. All right. The current carried by wire A is twice the current carried by wire B. Which wire has the higher current density? Thank you all. My philosophy is find ways to make your job fun. Like, as some of you already have jobs, some of you don't. Find ways to make your job fun. I like little ways to do that. Wire A, as current increases, current density has to increase or vice versa. They are proportional to one another with respect to the area that you're integrating over. So now we get to things that electrical engineers have been waiting to get to, like for the last 5 weeks, right? Resistance. If I could embed sound bites into a Menti presentation, I would. When I did this presentation at Harding, I would always import or have it play automatically via PowerPoint the March of the Resistance from Star Wars 7. It just works. I had this whole thing about how resistance was related to the resistance in Star Wars, but I can't remember it all off the top of my head. Resistance is defined as the ratio of potential drop to the current going through some circuit element. So you travel across a wire, right? Even a copper wire. you end up getting that there is current through the wire if the charge is moving through the wire, and you get a potential drop across the wire. Now it's going to be millivolt drops on the meter, but it's still non-zero drop, right? If it was a zero drop, then the charge wouldn't move to begin with. It requires a potential drop for the charges to want to move. Why? Why must there be a potential drop across, say, a low resistance wire for the charges to want to move? Think about it in terms of the things that we just took a test on Tuesday. Yeah, potential drop means electric field means force, right? So charges move in response to electric fields. For an electric field to be present, there has to be a potential drop. So good. We have a potential drop measuring, divided by the current going through it. That's going to be resistance. And this is going to be measured in ohms. Ohms are volts per amp. And we use that nice little omega sign there to be ohms. Now, one thing to note is that the resistance of materials need not be constant. But it's really handy when they are constant. For a material that is ohmic, it means that the resistance is constant over a wide range of currents and potential differences. In that case, we state Ohm's law, everyone's favorite, the nice, easy to work with, V equals IR, right? Doesn't get much simpler than that. V equals IR. The potential drop across something is going to be equal to I times the resistance R. If you want to know how much the potential has dropped, take I times how much the resistance is. And I think this, I'll get to your question in a second. I think this comes in, maybe if you're electrical engineering, you have a bit more intuition about this, but it's really, really tempting to say that the potential, or excuse me, the resistance of, say, a copper wire is going to be zero, but it's not zero. In fact, it's something really, really close to zero, but it's not zero. Say over 1 centimeter, 1 meter of wire, you get a resistance that's going to be on the order of milliohms or microohms. Really low, but not zero. Andrew, what was your question? I don't know. I'm not familiar with breakdown voltage. I'm sorry. My understanding of some of this stuff is limited to the nice little world of theoretical physics. I'll have to look it up. Are you talking about the, like when, through a dielectric? If you're talking about, and maybe we've got different working definitions here or something, but if you're talking about like through non-conductors, you know, the charge is going to flow through anyway. That was one of the questions on, you know, that one of the questions we did in class, right, where you get the breakdown of materials where the electric field is going to become so strong that charge moves through it anyway. I don't know in terms of the resistance, but yeah, that would definitely, it would be non-ohmic by that definition. What? Google says yes. Okay, great. Thank you, Google. Resistance is proportional to the dimensions of the current carrying object, where resistance is going to be resistivity times length over area. So resistance is resistivity times length over area. Now here's the thing. What that equation is saying is if you're dealing with, say, copper or silver or gold or whatever else you're dealing with, each one of those materials, assuming it's a pure material, is going to have a characteristic resistivity. The resistivity of copper is always going to be 8.11 times 10 to the minus 6 ohm meters. I don't know what it is off the top of my head. We'll see it on a problem here in just a second. But any copper is going to have that same resistivity. Same material means same resistivity. But the resistance will change as a function of length and area. So as something gets longer, its resistance goes up, right? You take a nice wire and you have a meter of it, it's going to be very low resistance. But you take a wire of the same material and you build a transmission line out of it that is going to be miles long, the resistance is going to go way up. Then you take the cross-sectional area. If you can increase the cross-sectional area, you give more room for the electrons to move around. You can deliver more electrons per length of wire, and you end up getting, with more area, lower resistance. That's why you use lower gauge wire, right? Lower gauge wire handles more current. It's not exactly the same thing, but it goes hand in hand. That bothers me, by the way. Lower gauge wire means bigger. It's just like in astrophysics. Lower magnitude means brighter source. Somewhere along the way, someone decided that was a good idea, and we ran with it. Two wires are made of the same material, but wire A is twice as long and has twice the radius of wire B. How does the resistance of A compare to B? Yeah, that's a good point. Where's wire C? It doesn't exist in this nice little weird universe. I got most of y'all on this one. Resistance of wire A is less than wire B. Why? Yeah, radius squared, right? So it's a bit of a trick question. I wasn't asking you that both the area and the length doubled. I said the radius and the length doubled. Area goes as radius squared. So we end up increasing the area more than we increase the length. And so the resistance of A is less than B. Hooray for trick questions, right? A note on wire gauge, only because we have electrical engineers in this class, and you have questions in your textbook and that pop up on Achieve that require you to know this. There's a convenient little... Convenient is hard to say. There is an equation that defines wire gauge. So you have, I love this, by the way. We use this in the American system, but it's based off of millimeters. 0.127 millimeters times 92, because why not have a 92 base system instead of a 10 base system or otherwise. Raised to the power 36 minus N, where N is your wire gauge, divided by 39, because 92, 36, and 39 are normal numbers that we work with every day. I don't know. I'm sure there's a very good reason we work with this. I don't know what it is, so I'm going to make fun of it, just like all people tend to do. We make fun of and we fear what we don't understand. This is, N is, are you talking about N? N is the wire gauge specifically. So if it's a 12 gauge wire, you'd have 36 minus 12. What? That's so random. Thank you. I appreciate that. Let's all make fun of the American wire gauge system because we don't understand it and we fear it. Do what? Yes. Send an email to, it's like Ron Swanson, right? Like, dear frozen yogurt, stop pretending to be ice cream and be better, right? Same thing.
How do you differentiate like zero gauge, double zero gauge?
Oh, don't ask me questions. We don't, zero gauge and double zero gauge, I truthfully don't know. We're only going to be working with 8, 10, 12, and 14 gauge in this class. Anything else that we're going to work with, we're going to know the diameter or the cross-sectional area or the radius. I only put this out of necessity because some of the problems in your textbook deal with this. I don't do it out of joy, or actually my soul dies a little bit when I see this equation on the slide. I'll look that up before the next class to try to have a better. Do what? Yeah, everybody's putting me on the spot today. Thank you. Is this just like payback for Tuesday's exam or something? I don't know. I like to pretend that wires don't exist, right? And escape to my nice little integrals with current density and imaginary areas. It's much easier for me to work with that as a physicist. And not so much for the electrical engineers. Resistivity, and therefore resistance, since resistance is based off of resistivity, is temperature dependent. So resistivity can change as temperature changes. You have resistivity at some baseline temperature. As far as we're concerned, or engineers are concerned, that's 20 degrees C. So roughly room temperature. So the resistivity at some temperature is equal to its baseline resistivity times 1 plus alpha. Alpha is the temperature coefficient of resistivity times the change in temperature from the baseline of 20 degrees. So if you go above 20 degrees C, you have higher resistivity and resistance. As you drop in temperature, your resistivity and thus your resistance gets better. Current flows better at lower temperatures. Current has more difficulty flowing as you go to higher temperatures. So you're building some sort of printed circuit board. You want to make sure, and the reason why we have heat sinks on things is because temperature causes issues with how your circuit will function. One of the reasons comes back to this. I'm sure there are more reasons that engineers can point out, but as far as I'm concerned, this is one of your reasons. Resistance changes with temperature. Right? As the resistance in Star Wars gets angrier, they become a little bit more hot under the collar, therefore they get stronger. Wait, that's the dark side, so that doesn't work. Never mind, forget that. I don't know. Yes, Maggie? Yes, so there is a table in your textbook, table 25.1, I think is what it is, is a table of table 25.1 would be resistivities, so it would be this value for different materials. I think table 25.2 is this for different materials. So it's going to be either given to you in a table, given to you in a problem, or you're going to be asked to solve for it. I think the question I put on last semester's exam said you have some unknown material and you had to solve for this. Yeah. A note on current density. From Ohm's law, we derive that V is equal to IR, but R is going to be resistivity length over area. And so V is going to be equal to the Jet Propulsion Lab. Nope, that's not right. J times rho times L. So current density times resistivity times length. But we learned in last unit that voltage is equal to electric field times length if the electric field is constant. Therefore, we state that you can calculate the electric field is equal to rho times current density, or electric field is rho times current density as a vector. So you know the resistivity of an object, you know its current density, or the current density through that object, then you can calculate the electric field. Or vice versa, you know the electric field inside the object, you know the object's resistivity, you know the current density then. We have notes all over the place, because now we have a note on current density. The previous relationship is also expressed as sigma E times J, where sigma is 1 over rho, and that's going to be the conductivity. I don't know, I always forget. Engineers, do y'all work with resistivities or conductivities, or you just don't care? You just know that you pull something off the rack and it's got a certain resistance because it's got the right banding that tells you so. Conductivity, resistivity, all those in favor say aye. What? Yeah, depends on the context is what I find. In the book that I taught out of for upper level E&M at Harding, the general rule of thumb was if its resistance was greater than 1, then you used resistivity. If its resistance was less than 1, you used conductivity. So meaning if it was a conductor, you used conductivity. And if it was a resistor, you used resistivity, but whatever. My favorite one is, what is it? You've got resistance is ohms, but conductance is Siemens in some context, but I've also seen it as mhos. That's my favorite. Conductivity is measured in mhos, which are inverse ohms, and it's just ohms spelled backward. I love finding that unit somewhere because I don't know. We're tired of coming up with units, so we're just going to spell the inverse unit backward and call it a unit. And I also just think of Harry, Curly, and Moe when I see mhos running around. And even better, mhos are just an upside down omega when you see it written out. So, woohoo! Go us. Hooray for creativity. Curious about your feedback on the exam, for those of you who are logged in. Yeah, that's what I thought. All right. I appreciate that feedback. Thank you. Still a few people going in. Well, thank you. I appreciate that. Any questions, either out loud or on the device, about the exam, about current, resistance, Star Wars? I don't know. Chuck Norris, that was the topic of discussion in Phys 1 on Tuesday. Thank you. That's exactly the context. These are really fun. All right, so questions. How do I feel about the exam? So far it looks like the average is going to be around a 56 or something like that. So yeah, I want it to be higher than that. I'll do what I can to work with you guys on that. But yeah, that's where we are right now. Where is wire 3? Shouldn't have started with that question, right? Where is wire 3? That's a good question. I wish I knew. I've been looking for it all day. Is it really turtles all the way down? Yes. I've looked into string theory, and basically if you map out the equations of string theory, you have to take the Fourier transform first, but the Fourier transform turns into turtles. So yeah, it's turtles all the way down. Thoughts on the weather recently? Man, we needed the rain. Will there be less questions on the next test? No, it'll be about the same, 24 and 10 questions. Is there any opportunity for extra credit? I try not to do that. There's not enough time, and this is a huge class, so we'll try to figure that out. Hopefully grade weighting works out. But remember, if you haven't taken the final exam with me, people tend to do well on that. Will there be any curve or partial credit? There may be a little bit of a curve, and partial credit is built into the test already. When I build the exam, it's already got partial credit, so depending if the correct answer was A and you guessed B, B might have been worth 2 out of 4 points. Curve, yeah, maybe, we'll see. What about the droid attack on the Wookiees? That's a very good question. I appreciate that, Kayada Mundi, whoever posted that. I think we'll send our best warrior in the entire Jedi Order to take care of that instead of worrying about other more pressing issues. When will the exam grades be posted? Right now it's looking like tomorrow because I've got to give an exam in Phys 1 today. Will the American wire gauge formula be on the formula sheet? No, because I don't like it, so you won't have a question that has to deal with that. I'm sorry. Oh yeah, probably tomorrow. Can we go over the last question? No, I still have people who still have to take the exam. Come ask me about it next week. Does the combined resistance allow you to solve for combined electric field and vice versa? Yeah, I'm thinking if you're going back, we related we said that rho times J, so resistivity times current density is equal to electric field, but resistivity, if you know the dimensions of your wire, then you can calculate resistance, so yes. But probably an easier way to calculate electric field from resistance is you know that V is equal to IR, right? And so from that case, V times length, so you just multiply by the length, and that would give you electric field. So V equals IR multiplied by length, that gives you electric field. There are 10 more questions that have popped up. I would like to ask why. My standard answer to that is because. I am scared. I'm sorry you feel that way. Maybe seek out the counseling center or something. I don't know. Oh, that's a good point. Yeah, the therapy dogs. Yeah, we'll have the therapy dogs. I'll email the officer and try to get them in next week or the week after that. That would be a lot of fun. Can we go over the questions of the pre-lectures? I have zero preparation for that because I put those together last semester, so I'll try to take a look at that before next time to be a little bit prepared. Whoever put that question, if you're not too scared because I agree that I'm happy to go over those, please send me a message on Canvas to remind me because I will forget to prepare for that before Tuesday's class. Did this test bring peace, freedom, justice, and security to my new empire? Why do you think I teach big classes? I'm trying to create a bunch of proselytes and acolytes to create a new order to the galaxy. We will rule all. Thank you for making class bearable. You're welcome. It's a lot of fun. What should a student do if they are completely lost? So please visit my office hours. If those times don't work for you, send me a message. I'm happy to try to make things work to the best of my ability. There is tutoring in the Student Success Center in the library. Is the library open again, by the way? Okay, the library's back open. So go there, talk to the tutors. We don't have pass for this class. I'm trying to push to get pass for Phys 2. I think that would be still beneficial. But talk to folks in the class to help get you back on track. Try to identify people in your lab or in your class who sit around you who feel a little bit stronger about this. If you're a whole pocket of people who are frustrated and lost, then come visit me together for my office hours. I meet most of the time when I get too many students. We go out to the common area and we meet together, and I'll do my best to help bring you guys up to speed. Professor Dave Explains has great videos on YouTube. The Organic Chemistry Tutor has great videos, and Khan Academy has great videos to help you get back on track. PhET, if you haven't played around with those demonstrations, PhET has great demonstrations to try to help you build intuition about this, but yeah, those would be my recommendations. I see that there are 12 additional questions that have popped up. We've got to move on, so if I didn't answer your question, please seek me out after class. Okay. Whew. Whirlwind. Quickly's not working. If you didn't catch that, please let them know about it, and we'll try to get this problem solved before the next class period. Whoever put the peace, freedom, and justice to my new empire, you made my day. That was really funny. A 10-gauge copper wire, let's just deal with it out the gate, carries a current equal to 20 amps. Assuming copper has one free electron per atom, calculate the drift speed of free electrons in the wire. Now, the real reason that I put this on here is because for homework problems and otherwise, this is going to become important about the one free electron per atom. That's great, but you need to know the atom density inside that wire. Otherwise, this doesn't help you at all. And so from that, you've got to remember from last semester and from chemistry that unconfusingly, we talked about the density of something as the variable rho as the mass per volume. So this would be mass density here, not resistivity. Is mass per volume. And we're going to have to relate that with Avogadro's number. You know that the mass of an object is going to be equal to an Avogadro number times the molar mass of that object. You've probably tried to forget that, but we'll deal with that here in a second. But ultimately, what we're trying to get to is I equals the number density times the charge of the carrier. So in that case, that's going to be the elementary charge times the drift velocity times the cross-sectional area A. So drift speed, drift velocity here is going to be current divided by N times E times A. Now you could use that convenient little formula, but it looks like I was wrong about how the tables were aligned. If you look in table 25-2 in your book, it tells you that the area of a 10-gauge copper wire is going to be equal to 5.621 square millimeters. So we have that just based off of it being a 10-gauge copper wire right here. We know the current I from this problem. That's the 20 amps given to us here. So the only thing that remains to be calculated, we know current, we know area, we know E is the elementary charge. That's the 1.602 times 10 to the minus 19 coulombs. So we have to calculate the number density. And number density, if we put these two equations together right here, we get that number density is going to be equal to the mass density, rho, times Avogadro's number divided by the molar mass, little m sub m. Well, the density of copper, which would have to be given to you, or you'd have to look it up in the table in your book, is going to be 8.92 grams per cubic centimeter. Avogadro's number, if you have tried to forget, is 6.022 times 10 to the 23, and that's atoms, which is just a count, so that's unitless per mole. All divided by the molar mass, which you can look up here on the periodic table, find copper, Cu, because it's cupric, right? Isn't that how it got its name? Comes out to be 546, and that's grams per mole. And this equals to a number density of 8.45 times 10 to the 22. I did some unit conversions here, sorry. Cubic millimeters. Yes, Bill? Number density is the count of how many things are present in a given volume.
Okay, so that's going to be the total number of atoms.
Yeah, so if I know the density of something, how much matter there is per volume, I know this is the mass per mole, then I have to consider how many moles are present as well. Or, I have to relate how many, how much Avogadro's number, let's see here, what am I trying to say? Here, I guess an additional equation that I needed to put up here is that number density is equal to number per volume, right? So number per volume is going to be equal to, I didn't write all of this down, and I always get frustrated trying to derive it live. Let's see here. Density is mass per volume, so that means N sub A times M sub M is equal to M, and then I've got that, so I've got M over V equals rho 1, 2, 2 divided by 1 gives me mass over volume per mass is equal to NA, wait. Yeah, NA and MM over, over density. The masses are going to divide out. So that gives me 1 over volume equals NAMM over rho. And now I want to relate those here. What am I forgetting? Total number is equal to Avogadro's, there it is. Avogadro's number times number of moles. Oh, I have this derivation written down in my office. But suffice it to say that if you know how much mass, so this would be grams per cubic centimeter. So I've got grams canceling out, so that's leaving me moles here. That's relating, density divided by molar mass is going to give me number of moles. And then if I want to relate how much there is of something to how many moles I have of it, I've got it here. Man, I'm just really struggling today. But number density just means the count of things in a given volume. Yes, that's exactly what it means. So I have almost a trillion number of electrons in a cubic millimeter of my copper wire. So now V sub D, taking this here, V sub D is going to be equal to the current, that's 20 amps, divided by the number density, oh, and that should be per cubic millimeter, right? So that would be 8.45 times 10 to the 22 per cubic millimeter times 1.602 times 10 to the minus 19 coulombs times the area we already found is 5.621 millimeters squared. Comes out to a velocity. I've got millimeters squared, cancels out these, and I'm just left with millimeters to the minus 1 power. I get amps is coulombs per second. So I get coulombs divides coulombs. So I've got per millimeters and per second, so they're going to have to switch places. So my answer is going to be 0.281 millimeters per second. And this is a pretty standard result, and what I'm trying to get to here is that inside of a copper wire, an individual atom moves a fraction of a millimeter every second, right? At 20, and that's at 20 amps. So really high current, it's still, and this is why we call it drift, one, because of the stochastic nature, two, because it just is insanely slow. Andrew, did you have a question? Yes, I did. That's what I said off to the side here. I switched to millimeters cubed from centimeters cubed, so I ended up having to change by, what would that be, a factor of 1,000? So it would have been 10 to the 25 per cubic centimeter. And then an additional factor of 1,000,000, 10 to the 31 per cubic meter. But I was going to millimeters since my American wire gauge was in millimeters squared, and because it's just insanely low to begin with. So I was trying to give this some sort of physical interpretation too. William? Eight point four five times 10 to the 22. Oh, so but we had grams cancel grams. We have atoms per mole, and we've got per moles cancel here. And what happens when you do this step right here, William? Do you get this result? Do you get that number based off of this being presumably in cubic centimeters? Because I could have written things down wrong in my solution. While he's doing that, did you have a question? You had the same thing?
It might have been the same thing, but I believe that is when you have it there in millimeters, it's in centimeters.
It's in centimeters? Okay. That's not unlikely that I made a mistake copying this down. What? Okay, so divide by 1,000 would be 10 to the 19 per cubic millimeter. Yeah. So that, let me make a note of that so I remember to fix that later on. I'll take a look at it after class and I'll get the correct solution posted on Canvas. Okay. Let's look at one that's not got American wire gauge in it. An accelerator produces a beam of protons with a circular cross-section that is 2 millimeters in diameter and has a current of 1 milliamp. The current density is uniformly distributed such that throughout the beam. The kinetic energy of each proton is 20 mega electron volts. The beam strikes a metal target and is absorbed by the target. What is the number density of protons in the beam? How many protons strike the target each minute? And what is the magnitude of the current density in this beam? Okay. So our equation for current is going to be equal to N times E times V sub D times A. And area is for something of constant diameter, pi r squared, or that's pi times diameter over 2 squared, or that's pi d squared over 4. And so in part A, if we're trying to calculate the number density here, divide by EVA, so current over EVA. I can calculate my area from this value. I know the charge, I know the current is 1 milliamp. How do I calculate the drift speed here? ½ mv squared. So we know how much energy each of the protons have. They have 20 mega electron volts in terms of their kinetic energy. So kinetic energy K is going to be equal to 1/2 mv squared. And don't forget that 1 EV is equal to 1.602 times 10 to the minus 19 joules. So the velocity is going to be equal to root 2k over m. The mass of a proton, I don't have that one written down here. The mass of a proton is, no, that's an electron. It's on the order of 10 to the minus 27 kilograms. I at least remember that much. What is it? 1.67 times 10 to the minus 27 kilograms. Remember the order of magnitude. So I've got I divided by E times the square root of 2K over M times pi d squared over 4. And if you convert units and plug everything back in, this ends up giving you a number density of 3.21 times 10 to the minus, 10 to the plus 13 per cubic meter. So this is actually a really low number density. The previous answer that we got on the last slide was 10 to the 22. So in free space, where these electrons are flying through the air, the number density is much lower than it was before. 3.21 times 10 to the 13 per cubic meter. And if you wanted to calculate as a checkpoint, 6.19 times 10 to the 7 meters per second. So we have a bit of a problem here because that is on the cusp of relativistic. That's 20% the speed of light. How many protons strike the target each minute? The number striking the target each minute, you could take your velocity here, would probably be the easiest way to do it. Velocity times time, I think would be the easy. That's not right. Velocity times time. That would be, no, how far it goes. That's not right. The way I have written down, which is as good as any, the number that strikes the target is going to be equal to the number of charges divided, the total charge divided by the charge carrier, and the total charge is going to be I delta T divided by E. So 3.21 times 10 to the 13, nope, that's not right. Current is 1.0 times 10 to the minus 3 amps times a time of 60 seconds, all divided by a charge carrier of 1.602 times 10 to the minus 19 coulombs. And this comes out to be all the units cancel here, so this comes out to be 3.74 times 10 to the 17. I'm trying to think if there's a way that you can calculate that just based off of number density, but I think that would be more complicated. But we know the current that arrives on the plate, current is charge per second, so we multiply by the total time, that gives us total charge. Divide by how many charges there are there, or how much charge each carrier has, that gives us number. Part C, what is the magnitude of the current density? Fortunately, since it says here that this is distributed uniformly, so uniformly distributed, that means current over area, or current divided by pi d squared over 4. This comes out to be a current density of 318 amps per square meter. Or that's 331.8. Nah, let's not even write that up there. 318 amps per square meter. Yeah. A lot of, even a small current divided over a really tiny area gives you a pretty high current density. Any questions? We'll do resistance and resistivity on Tuesday. It's been a long week. Y'all took a test this week. Let's leave 13 minutes early.